Hi everyone, this is physics seminar presented by PK Geeta Priya of 2nd BSc Chemistry from Dr. SNS Rajalakshmi College of Arts and Science. Nuclear magnetic resonance. Actually, nuclear magnetic resonance is a method. This method is a physical observation of which nuclei is strong constant magnetic field are permitted by a weak oscillating magnetic field, which is in the near field and therefore not involving magnetic waves, and respond by producing an electromagnetic signal with a frequency characteristic of the magnetic field at the nucleus. This process of nuclear magnetic resonance process occurs near resonance when the oscillating frequency matches the intrinsic frequency of the nuclei, which depends on the strength of the static magnetic field, the chemical environment, and the magnetic properties of the isotope involved. In practical application with static magnetic fields up to 20 Tesla, the frequency is similar to VHF and UHF television broadcast, which ranges up to 60 to 1000 MHz. NMR results from specific magnetic properties of the certain atomic nuclei. Nuclear magnetic resonance spectroscopy is widely used to determine the structure of organic molecules in solutions and study molecular physics, crystals, as well as non-crystalline materials. This NMR, that is nuclear magnetic resonance, is also routinely used in advanced medical imaging techniques such as in magnetic resonance imaging, which can also be called as MRI in short form. This is the pictographic representation of NMR. A key feature of NMR is that the resonance frequency of a particular sample substance is usually directly proportional to the strength of the applied magnetic field. In this feature that is exploited in imaging techniques, if a sample is placed in a non-uniform magnetic field, then the resonant frequencies of the sample's nuclei depend on where the field they are located. Since the resolution of the imaging technique depends upon the magnitude of the magnetic field gradient, many efforts are made to develop increased gradient field strength. Next, we are going to see about the principles. Actually, this principle of NMR usually involves three sequential steps. The first sequential step is the alignment. Alignment means which is called as polarization of the magnetic nuclear spins is an applied constant magnetic field B0. The next one is the permutation of this alignment of the nuclear spins by a weak oscillating magnetic field, usually referred to as a radio frequency, that is RF pulse. The oscillation frequency required for significant permutation is dependent upon the static magnetic field, which is called as B0, and the nuclei of observation. The detection of NMR signal during or after the RF pulse due to the voltage induced in the detection coil by precession of the nuclear spins around B0. After an RF pulse, precession usually occurs with the nucleus intrinsic gamma frequency, and in itself does not involve transitions between spin states or energy levels. Next, we are going to see about the applications of NMR. This NMR is used in various fields. First, we'll see about in medicinal field. NMR is extensively used in medicine in the form of magnetic resonance imaging. NMR is used industrially mainly for routine analysis of chemicals. The technique is also used, for example, to measure the ratio between water and fat in food, monitor to flow the corrosive fluids in pipes, or to study molecular structures such as catalyst. This is the pictographic representation of NMR, which is used in the medicine field. The application of nuclear magnetic resonance best known to the general public is magnetic resonance imaging for medical diagnosis and medicine resonance microscopy in research settings. However, it is widely used in biochemical studies, notably in NMR spectroscopy such as proton NMR, carbon-13 NMR, deuterium NMR, and phosphorus-31 NMR. Biochemical information can also be obtained from living tissue. Example, human brain tumors, which in the technique is known as vivo magnetic resonance spectroscopy or chemical shift NMR microscopy. Next, we are going to see how the NMR is used in the field of chemistry. By studying the peaks of nuclear magnetic resonance spectra, chemists can determine the structure of many compounds. It can be a very selective technique distinguishing among many atoms within a molecule or collection of molecules of the same type but which differ only in terms in their local chemical environment. NMR spectroscopy is used to unambiguously identify known and novel compounds, and such as is usually required by scientific journals for identity confirmation of synthesized new compounds. See the articles of carbon-13 NMR and proton NMR for detailed discussion. Next, we are going to see how the NMR is used in the field of purity determination. While NMR is primarily used for the structural determination, it can also be used for purity determination provided that the structure and molecular weight of the compound is known. This technique requires the use of an internal standard of the known purity. Typically, the standard will have high molecular weight to facilitate accurate weighing, but relatively few protons, such as to give clear peak for later integration. Example 1245 tetrachloro 3 nitrobenzene. Accurately weight proportions of the standard and sample are combined and analyzed by NMR. Suitable peaks for both compounds are selected and the purity of the sample is determined via equation. Next, we are going to see how the NMR is used in the field of sequential and molecular motions. In addition to providing static information on molecules by determining their 3D structures, one of the remarkable advantages of NMR over X-ray crystallography is that it can be used to obtain important dynamic information. This is due to the orientation dependence of the chemical shift, dipole coupling, or electric quadrupole coupling contributions to the instantaneous NMR frequency in an anisotropic molecular environment. Next, data accuracy in the petroleum industry. NMR logging, a subcategory of electromagnetic logging, measures the induced magnetic moment of hydrogen nuclei, that is protons, contained within the nucleic field, pore space of porous media, that is reservoir rocks. Unlike conventional logging measurements, example acoustic density, neutron and resistivity, which respond to both the rock matrix and fluid properties, are strongly dependent on mineralogy, NMR logging measurements respond to the presence of hydrogen. Coming to the conclusion, this NMR is also applied in many other fields. The application plays a very important role, thus magnetic resonance, and the applications are well explained in this seminar. Thank you.